Hello and welcome to the next episode of the Klingberg Wing Mark II development. I'm Raul Klingberg, your host. You haven't seen me in a while. That's because I've been down south working on some cool stuff for the defense industry in a remote, undisclosed desert location. But I'm back now. I'm back to do stuff that's more fun, less profitable, more fun. Anyway, so I had put out questions to some of my viewers about what are you looking for in a hang glider for the future going forward? And the responses I got surprised me a little. They were not focused on performance so much as usability. Most of the comments were on, gee, I'd like it to be more transportable, and I'd like to be able to get into and out of tight remote locations. And it'd be great if it were lighter. You know, our gliders have gotten really heavy, and boy, transportability, light, yeah, they just seem to go together. And I'm thinking, gosh, do they know what they're saying? As they typed this out, do they realize what they're typing? They might as well just type paraglider at the end of that because it's half the weight, unless you get a really lightweight Vol Biv design that's super light. They're lightweight, they're easy to transport. You get them into and out of tight locations. And gee, what's your issue? Or you just go buy one of those. And of course, that's part of the explanation about why we've had such a drop off in popularity of hang gliding, is because the performance of paragliders have been catching up with hang gliders rapidly. But I believe that we're at a peak right now or near a peak, and they're not going to ever match a hang glider in performance. But pretty close enough to obviate the differences in performance in a trade-off for transportability and usability. So I thought, well, geez, there's some people that are sticking with hang gliding, and they do it for a reason, and they wanted to have some of the qualities of a paraglider. And I thought, why would they want that? Like, okay, I fly both, so I think I understand both groups. When I started flying paragliders, I just didn't like the concept that my wing that I'm flying on could collapse in flight. Now, things have gotten much better since the mid 90s, and they're highly stable paragliders now. They don't really tend to collapse that much. And when they do, there's really a rapid recovery. So a lot of that issue has gone away. But it still exists to some extent. I've never had a collapse that caused me any concern at all. I've had some ruffling of my fabric, but that's about all. So I guess the other issue would be the ability to go fast. Hang gliders, you can pull in, you have direct pitch control, and you can go fast. Yes, we have speed bars on paragliders, but I push on my speed bar, and what do I get? A whole whopping extra 2 miles an hour. And, 2 miles an hour is, spitting in the ocean. It's really, a hang glider will get up and go 40 miles an hour plus. My new design, once I get it fully functional, that should easily do 70 miles an hour. So, okay, pitch control. So if you're really enamored of the ability to have positive pitch control on a hang glider, and you can do more aerobatics and stuff like that. Okay, so how do we make them more transportable and lighter weight and maintain durability? Because that's a part of usability. And I thought about that for a while, and I said, really the only area to work on is weight, because the transportability issue has been resolved in several designs. You can go out and get them now, or you can modify a current one where the tubing comes apart in sections, and you can fold it up into a relatively small bag that you can easily load on an airliner as excess baggage and go that way. So that issue's been dealt with, but the weight really hasn't. People might think it has, but hang gliders are heavy. 80 pounds, 85 pounds, 90 pounds, maybe more. Flex wings have gotten as heavy as some rigid wings, which is really pretty impressive in my mind. You don't do that just standing still. You have to put some effort into making a flex wing as heavy as a rigid wing, and the rigid wings have gotten lighter. So, interesting problem. Now, we have two areas that we can attack relative to the weight of hang gliders, and that would be the sail or the fabric and the framework, the tubing. Tubing has been somewhat dealt with. There are some gliders out there that have a significant amount of carbon fiber in them. And, well, there's attending costs with that. They're expensive. So how much do you want it to be lightweight? You better want your lightweight a lot, because it's going to cost you a lot to get lighter. But it's doable, I think. And as I thought through this, I thought, okay, lighter weight, how do you do that? Lighter weight tubing. What's the problem with some of the carbon fiber they have now? Well, they've backed themselves into the classic carbon fiber aluminum trade-off corner. And engineers run into this all the time, and we have a derogatory term for it in the engineering world. It's called black aluminum. That is where somebody just simply substituted carbon fiber for aluminum, and they're running essentially the same wall thicknesses, the same type of structure, and all you've done is replicate the aluminum structure in carbon fiber. And the drawback to that is carbon fiber is heavier than aluminum. It's fantastically stronger, but it's heavier. So if you just do a one-to-one swap, it's not going to be lighter. It's actually going to be heavier. So to design in carbon fiber and lower weight, you got to understand the idiosyncrasies of carbon fiber and use those to your advantage when you do the design. And that requires special design techniques, maybe some new ideas. And you need to stay aware of a key factor, which I'm going to talk about here in a moment. But let me show you this first. As you can see, I'm out in the shop. I'm in the process of building new wingtip panels for my Klingberg Wing Mark II, and there'll be a video coming up about why I'm doing that, and I'll show you some of that build. But let's talk about tubing for a moment. Here's several pieces of carbon fiber tubing that I have here that I made. This is 3 layers of 5.6 ounce fabric on an 1.5-inch mandrel. And this weighs, I got to pull up the other one. Stand by. Here, let's get the other one. Here, 1.67 ounces per foot. Wow, it's pretty light. It's the wall thickness is 30 thousandths. And here's the interesting thing. This may or may not have the bending stiffness that we want, but it's certainly got way more tensile strength and probably way more compressive strength than an aluminum tube of the same wall thickness. This is just a phenomenally strong piece of tubing. Bending strength, well, there's bending stiffness and bending strength, but the bending strength on this, I don't know, I've never characterized it. I'd have to take a length of aluminum tubing, same wall thickness, and a length of this, and hang weights on them and find out who bends more for a given load. Carbon fiber is well known to be extremely stiff. So this would probably exceed aluminum tubing of the same wall thickness and stiffness. And it's a lot lighter. But is it strong enough? Probably. Is it lighter? Oh. Well, if I got aluminum tubing, that's 3/10 wall thickness, same as this. This is 3 layers of 6 ounce fabric. The aluminum tube might actually be lighter than this. So by the time, okay, let's take the weight of this down to what the aluminum tubing is. Take down the wall thickness. Maybe we take it down to 2/10, 2 layers, 2.5 layers. Can we do a half layer? That'd be kind of weird. Tubing stronger on one side than the other. We probably don't want to do that. We can tailor the tubing. If it takes bending in one direction, we can stiffen it in one direction, leave the other direction a little softer. We can do stuff like that. But you don't want to do halvesies. That'd be such an asymmetrical structure as not to be a good idea. Okay, so we take it down to 2/10. And so that's going to take out a third of the weight here. 1 point, we'll just call it 1.6. So that's going to take out 0.8 of an ounce per foot. Well, that's significant. Not quite that much. Let's see. The 16.3, about 0.48 ounces per foot is what it'll take out. Would that work? Can we substitute just carbon fiber tubing that has smaller wall thickness? Everything else is the same, and make it so that it's the same strength as aluminum tubing and has the same stiffness characteristics as aluminum tubing, but is lighter than aluminum. And from working with this material, I can tell you that's going to be a very tricky spot to hit. And that's because of another problem. By the time I took this tubing down to the same strength as aluminum tubing, I'm going to run into what's called its buckling limit. And buckling limit is a heck of a problem that we deal with in ultralight composite structures or ultralight structures of any kind, is that, now the structure it's strong enough in tensile strength, compressive strength, bending strength, strong enough in all of those, but it'll buckle. And once it buckles, all the strength's gone. Poof. And that's a problem. So there's a buckling limit. So many composite structures for ultralight aircraft are built to a buckling limit, not necessarily some other strength limit like tensile strength, compressive strength, bending. And hence, the structure comes out heavier than it needs to be for its strength. So we end up with something that might be a little bit lighter, hell of a lot stronger, way stronger than we need, and maybe we've lost some durability. So what if we take it to its logical limit and say, okay, I'm going to make tubing that is the same strength as aluminum tubing, and it's going to be really light. And screw this issue with the buckling limit. Raul doesn't know what he's talking about. I'll just put some bulkheads in here. Styrofoam bulkheads, that'll keep it from buckling. Well, let me do a little demonstration for you here. Here's a piece of 1.5-inch diameter tubing that I made that is 1 layer thick of 6-ounce cloth. And this is about, what did I have on this? There it is. This is 1/2 ounce per foot. This is going to be lighter than aluminum tubing of the same diameter, of some other thicker wall thickness, and it'll probably have the strength of aluminum tubing that might be 30 thousandths. Before when I say tenths, I'll put a little thing up on the screen. Not tenths, thousandths, 30 thousandths. So this is probably as strong as aluminum tubing that is 30 to 50 thousandths wall thickness, but it's only 10 thousandths of an inch. Very, very thin, 1 layer. And in bending, it probably would be strong enough if we could keep it from buckling. But what happens is by the time you put enough bulkheads in here, even if they're styrofoam, you go all the trouble to glue bulkheads in here, and you'll prevent the local buckling, but now the weight's back up, and it's not because of the styrofoam, it's because of all the epoxy you used to glue them in there. So that you end up chasing your tail on those. And I've seen some people do that with human-powered aircraft. So let me show you why buckling is such a problem here. Watch close. I'm only going to do it once. But look, right in my hand, I can take this and just do that. And your tubing is history. It has no strength left in it. So with the mere grip of my hand, I can collapse and fracture this tubing, and it's useless. It might as well be tissue paper. So that's a buckling limit. You don't want to mess around with the buckling limit. It'll get you in a lot of trouble. You got to avoid the buckling limit. You got to stay away from it and maintain really thin wall thicknesses, or limit the amount of composite material you use to just the amount of material that you need to get the strength you want and stop it from buckling. And putting in a bunch of bulkheads is generally not a good answer because of all the epoxy you use. So how do we use the epoxy that we're already using to lay up the tubing to make it stiff, to glue something in there? Can I wrap this on a mandrel with a bunch of bulkheads in it? Oh, that'd be weird. How do you get it off the mandrel? That doesn't make any sense. Well, we have another solution available to us, and I've used that to make some tubing. And let me tell you about that solution a little bit here. Let me see if I can pull up something. As you know, let me pull up one of my D-tubes here. This is a junky old piece of D-tube that didn't come out very good. But this is a D-tube section for the tip panels of my current wing. And if you've been following with me, you know that this is a sandwich panel construction. It has carbon fiber on the inside, very thin spread toe carbon fiber on the inside. I think that's about 3 ounces per square yard. And then it has a layer of Aerex foam at about 3 pounds per cubic foot, and it's a 1/16 of an inch thick. And then on the outside, I got one layer of 3-ounce fiberglass, 120 weave on that. Very fine weave, is a smooth finish. Sandwich panel prevents buckling. Certainly increases your critical buckling length so that you can make it a reasonable structure with a limited number of ribs or longerons. Sandwich panel construction is like magic. And it's been used for decades and decades and decades and works great, especially for composite structures. So it occurred to me one day, why don't I make sandwich panel tubing? Wow, wouldn't that be cool? Well, I tell you, I had a dickens of a time getting the foam around this leading edge radius here. How am I going to get it around a tight piece of tubing, 1-inch diameter tubing, which is used in many places? 1.5 inch, 2-inch diameter tubing might be a little bit easier. But then how do you deal with the seam? They're just going to come together and butt together like this? And how am I going to keep that? And if you've ever played with the foam, it's just, and I went around in my head for a long time. How do I do that? How do I do that? And I played with the materials like, oh, that's not going to work. That's not going to work. And I eventually came up with a solution. And those of you who've asked about, I want my glider to be really lightweight, I was like, well, apparently you didn't watch my earlier videos because the answer's already there. All you have to do is watch my earlier videos. I already gave you the answer on how to get a really light hang glider. And that's sandwich panel tubing, because eventually I solved that problem and I demonstrated it for everybody that watches my channel. If you look at the earlier videos, you'll find it. And I tell you exactly how to make sandwich panel tubing. And it comes out like this. Here's a piece of it. This is 1/16 Aerex foam. And on the inside is one layer of 3-ounce fiberglass. And on the outside is one layer of 1.5-ounce fiberglass. And this slightly over 1-inch diameter tubing only weighs 3/4 of an ounce per foot. And it's phenomenally strong. This is only a little bit heavier than the carbon fiber tubing that I collapsed into nothingness. And this stuff, you can grip it in your hands. Go ahead, try to crush it, Rob. Try to crush it. I'm squeezing it in as hard as I can, and it barely flexes. It has the stiffness. The sandwich panel has created a stiffness such that you can't buckle it. It's almost like putting bulkheads in here, but it's hollow. You can look right through it, just like that. So, and relatively straightforward to make this stuff. Now, if you're smart this time and you want to figure out how to make your hang glider a lot lighter, you'll go to the description in this video, click on the link, and go watch the demonstration of how to make this tubing. Can we substitute this straight up for aluminum tubing in hang gliders? And it can be anything. It could be carbon fiber on the inside, carbon fiber on the outside, Kevlar, mix of this and that and everything. You'd have to play with this methodology to create tubing that has all of the mechanical properties we want and be a lot lighter than aluminum. I personally believe you could take half of the aluminum frame weight out of a hang glider. You'd probably take out 20 pounds, 30 pounds, and that's significant. If you got an 80-pound glider and you take 30 pounds out of it, holy cow, you're almost back to the early Regalo days. Yeah, back then we were 35, 38 pounds. But gosh, if you had a modern flex wing that only weighed 50 pounds and you could take it apart for transportation, would that not be cool? Yes, it would. And somebody could already be working on that answer if they watched my early videos. Yeah, it's a lot of videos, 100 and some odd videos, but sometimes it might pay off to go back and look at them or click on that link that I have down below and go watch it. Now, I hit upon a critical item there, characterizing the physical properties of this stuff. I've never done it. I have used this tubing in the pilot's cage of my current glider, and it held up through that first bad flight where I had a wonderful takeoff, bad landing, and crunched the pilot's cage. And this stuff didn't break. In fact, when I finally broke it, it's because I sat on it with no support underneath. And I put a load on it that it was never designed to carry. And I snapped it in half when I sat on it, my big fat butt. And there we go. And if it would have been aluminum tubing, I would have bent it. It just wasn't meant for doing that job. It wasn't a seat. Okay, so that said, a lot of work would be involved in fully characterizing this tubing. You have to make a bunch of different types, and then you have to go load them in some consistent, viable, logical, robust engineering style. You have to go do engineering testing on it. And you have to do this repeatedly over a dozen samples, 24 samples, and then you got different mixes of cloth, different foam thicknesses. Wow, you might need to make 30 or 40 little pieces of tubing. And when I say little, they have to be about 4 foot long in order to give reasonable characteristics in terms of bending and so forth. It's some work involved. Well, I'm already building a glider, and I'm thinking about other glider designs. I don't fly flex wings. There's no personal motivation for me to go solve this problem. But those of you out there who want lighter weight, more portable hang gliders, and somebody out there who's done some composites work, even on boats, doesn't have to be on aircraft, just know how to work with composites, go do this. Take up the task. Go make a dozen pieces of tubing and start testing and post a video so we can all see it and find out what are the mechanical characteristics of this style of tubing, so that maybe we can begin to think about using it on flex-wing aircraft. Would it be affordable? I don't know. What do you call affordable? This is the airplane world. As soon as you say airplane, you shouldn't use aircraft and affordable in the same sentence anyway. It's if you want it, you got to pay for it. This would be handmade tubing. And anytime you say handmade, you just got the $4 signs on there. It would not be cheap. But it's phenomenally lightweight, phenomenally strong. And I already invented a way of making it. So you don't even have to dream up a way of making this tubing. And by the way, this could be automated. You could build a machine to do this special wrap. So, hey, here's your chance, Internet. Somebody out there with the composites experience and a little bit of spare time on their hands, go out and make a bunch of this stuff and tell us all what its physical properties are so we can go and design aircraft to use it. And that would be a huge benefit to everybody. And there's certainly some demand for it, I think. It'd be fascinating to take some old single surface flex wing, rip the aluminum tubing out of it, and maybe just on one leading edge, or maybe the keel, say, I'm going to do one piece of tubing that's Rawls funky sandwich panel tubing and see how it performs. But I wouldn't do that until you have some of the physical characteristics defined. It's not an area for guesswork. You cannot guess, and it's very, very difficult to calculate accurately the Euler buckling of this construct because of the foam, the weird spiral wrap, how you put the fabric on here, how good was the wet out. There's too many variables. You could sit down and do a calculation and figure out what the bending stiffness of this is. And I assure you, your answer will be wrong. Wrong to a degree that you wouldn't want to trust it to design an aircraft around it. You need to go out and make tubing and test it to failure and find out how strong it is. So that's the challenge I leave with you, all you internet peoples. Somebody take up this task, or some group, some club, and go do this job for us, because there's no manufacturer out there that's going to do it for you, because there's no money in this. There's no profit. So if you want this, you got to do it for yourself. I'm already busy. I already gave you methodology for doing it. Go watch that video and come back in a month or so and tell us what we really have. Now, there are some limits to this. You could make a large leading edge tube quite easily out of this stuff. And it could be plenty strong, but it might not be stiff enough. By the time we get the weight down, we might lose a bending stiffness. In other words, what we would call specific stiffness. Or it's going to bend differently. And our sails on flex wings are cut to accommodate the expected bending and flex of the airframe. They compensate for that, and they do it magnificently on current designs and maintain beautiful airfoils, great shape, and allow the aluminum tubing to flex. Would this stuff flex the same way? No, it's not going to. So it would cause the need for a recalculation on the sails themselves to compensate for the amount of flex that's in this tubing as opposed to aluminum tubing. But we could save a ton of weight, a lot of weight. And to get that savings, well, you just have to fork over some dollars, and somebody's got to do some experimentation. So there we go. Somebody out there, please raise your hand and say, I'll do it, and then get on with it. Don't take a year to do it. Don't take 2 years. Don't take 6 months. Just dive right in, and I'll make you a special offer. Here's the special offer at the end of the video. If you contact me in the comments and say, hey, Raul, I have the expertise to do this work. I can do the engineering that's involved. I can do the building, and I get this stuff characterized. But where the heck do you get the AirX foam? I'll say, oh, you get it in Germany. And you'll say, isn't that expensive? And I will say, yes, very expensive. But if you're the right character, if you have the capabilities and the commitment to do this, I will donate some of my AirX foam that I have in stock. A sheet or two of that, I'll roll it up and send it to you, and you get this job done. And we'll all thank you. And we'll give you an official Raul Klingberg attaboy. And that's worth the paper it's written on. Anyway, so it's been neat talking about this. I have a bunch more videos coming because I got stuff backlogged. So I ask you to stick with me. And if you like the work that I do and you want to continue, if you want me to continue inventing new methodologies for making tubing and stuff like that, please go over to my Patreon channel. The link's down below, along with the link to the video I've been yammering about. And throw a nickel in the pile, you know. We're not talking about a lot of money, but every little bit coming in helps. It helps pay for the materials that I use to do all of this work. And the patrons I have supporting me now have been fantastic, been with me for years, and have really made this stuff doable. And I need continued support from all of you. So please don't just sit back and suck up all of this wonderful engineering work for free. Be part of the plan. Throw a nickel in the pile. Go over to Patreon. Join the group. And if you're lucky enough, and I got a couple of hats left, you sign up as a patron, I'll send you a free hat, just like this. Okay, cool. Thanks for coming. And in the meantime, as I always say, fly safe and bye for now.